All right, next up in section 13.4, we're going to look at problem number 3, where we're asked to find all of the first and second order partial derivatives for the function f of xy is the natural log of the square root of 3x squared plus 2y squared. Okay, so if I'm going to differentiate a function like this, I think first it's a good idea to just notice that this square root really is an exponent of 1/2. So this is the same thing as saying that our function f of xy, using the property of exponents, that says that 1/2 can come out front. This is really just 1/2 times the natural log of 3x squared plus 2y squared. Okay, so that'll make the derivative part a little bit easier with respect to the chain rule. So let's go ahead and compute the first order derivative. So we can go ahead and do, say, partial f partial x. And so for this, well, I'm differentiating a log function, so that's going to be 1/2 times 1 over what's inside the log. So that's 3x squared plus 2y squared. And then I have to apply the chain rule. So I have to differentiate what's inside the log with respect to x here. And that's going to give me just a 6x. Right? The derivative of 2y squared would be 0. So that'd be times 6x. And so putting this all together, notice the 2 and the 6 can simplify. So I'm going to get a 3x over a 3x squared plus 2y squared. All right, so that would be our x derivative. We can carry over here and do the y derivative of f. So it's going to be 1/2 times 1 over what's inside the log. And then from the chain rule, I need to multiply by the derivative of what's inside the log with respect to y. So that's just going to give us a 4y here. Okay, and again, the 4 and the 2 will simplify, so we get a 2y over 3x squared plus 2y squared. All right, great. So not too bad there for the first order derivatives. So let's now move on and check out maybe computing, say, the xx derivative. So this would be the xx derivative. So for that, what I want to do is compute the x derivative of what? Well, the x derivative of f, which we computed here to be 3x over 3x squared plus 2y squared. Okay, so to carry this out, this is an x derivative here, and I see an x in the numerator and the denominator, so that's going to tell me I need to use the quotient rule. So put a little note here, we're using the quotient rule. And so I'm going to do the low function, my 3x squared plus 2y squared times, so low d high, so the derivative of 3x with respect to x would be 3, minus high, so that'd be 3x times the derivative of low with respect to x. That's going to give me a 6x. And then I'm going to divide that by the square of what's below. So that'd be 3x squared plus 2y squared quantity squared. All right, so let's clean this up a little bit. So we're going to get here what? Well, for the x squared terms, I'm going to have a 9x squared, and when I distribute that 3, and then I'm subtracting an 18x squared. So that's going to give me a minus 9x squared. all in all. And then for the y squared part, here I'll go ahead and record this here. So I said 9x squared minus 18, so that'd be minus 9x squared. And then I have this plus 6 y squared, and then I'm again dividing by 3x squared plus 2y squared quantity squared. All right, great. So that would be my x derivative there. Next up, we can do the y derivative. Pretty similar to the xx. So this is the y derivative of the y derivative of f, which we computed up here to be 2y over 3x squared plus 2y squared. And so when we do that, again, I'm going to need to use the quotient rule because I have a y in the numerator and denominator. And so I'm going to get the low function, 3x squared plus 2y squared times the derivative, which is 2, minus high, which is 2y, times the derivative of the low with respect to y would give me a 4y. And then I'm going to divide all of that by the square of what's below. So that'd be 3x squared plus 2y squared, quantity squared. So now let's clean this up. So for my x squared terms, I'm going to have a 6x squared. And then for the y squared terms, I'm going to have 4y squared minus, and then this is an 8y squared, so that'd be a minus 4y squared. And then I'm dividing all of that by 3x squared plus 2y squared quantity squared. Alright, so that would be my y derivative. Okay, and so then lastly, we need to compute the mixed partials, right? And one benefit here of Clairaut's theorem is that we actually just need to compute either the xy or the yx. They're going to be the same because this function is, well, sufficiently nice. Again, you really don't have to worry about that. For functions in this course, you really can just make the assumption that these two derivatives, the xy and the yx, are going to be the same. Okay. I'll post on Canvas on that note an example of where it fails, but again, we're not going to be working with those really in any capacity. So, all right, so now let's go ahead and just compute one of these. So, for example, I could compute the xy derivative. Okay, so this would be like the x derivative of the y derivative of f. And again, we computed that to be 2y over 3x squared plus 2y squared. All right, and now notice here, I'm taking an x derivative and I don't have an x up in the numerator. I just have an x in the denominator. So if I think about this expression in parentheses as 2y times 3x squared plus 2y squared to the negative first power, since I'm differentiating with respect to x, right, the 2y out in front is just constant. So I'm just going to go ahead and differentiate this thing using the chain rule. Okay, so to do that, we're going to get the following. Okay, the negative one's going to come down, and I'll get negative 2y times the quantity, 3x squared plus 2y squared to the negative second power. And then I need to multiply by the derivative of what's inside, right, the parentheses, 3x squared plus 2y squared, with respect to x, and that's going to give me a 6x. Okay, so when all is said and done here, combining, I'm going to get a minus, well, 12, because of the 2 and the 6 multiply, so minus 12xy, and then that's being divided by the square of the term 3x squared minus 2y squared, and then the quantity squared. Okay, so this would be the expression for both mixed particles. Now, I did the x derivative of the y derivative. I encourage you to do the y derivative of the x derivative and just to convince yourself you're going to get this same expression here. But all right, that is going to do it for this example.